Hello everyone, and thanks for joining today. My name is Dan Baeder, and I'm a manager and data scientist here at Deloitte Consulting in the United States. I'm joined this morning by Dr. George Panteras, who is also a data scientist and manager in applied AI here at Deloitte. Together, we lead the data science efforts on an advanced simulation and modeling platform built at Deloitte called FutureScape. We're excited today to share what FutureScape is, how we're using it to drive insights for clients across many domains, and how we're using advanced spatial data science techniques to enhance data processing, generation, and visualization of simulation inputs and outputs. We've broken the presentation into two components. First, we'll introduce FutureScape, explain how we build a simulation, and show a demonstration of the platform in action. Then, we'll pivot to specifically address the spatial data science work we're doing to generate and visualize spatial-temporal data. Let's start by thinking about two big classes of problems. On one hand, we have cases where an organization has data from which they want to extract some insight. They might have a lot of data or disorganized data or data streaming in with higher velocity than they're capable of dealing with. In all these instances, the issue is one of finding the right technologies or techniques to uncover the signal and the noise. Now, on the other hand, we have cases where an organization has problems that they need answers to, but the data necessary to solve those problems doesn't exist. We call these what-if questions. Our clients, like metropolitan planning organizations, departments of transportation, and other public agencies, face these questions all the time. What if our region is disrupted by a natural disaster? What if we build a new light rail line? What if we raise tolls? What will the impact of these events or changes be? So, these organizations have a choice. They could build or prototype their proposals to gauge the impact, but this is tremendously costly in terms of time spent, dollars spent, and overall risk. Alternatively, they can build models or simulations to explore the impact of their proposals in a digital test bed with much lower costs across the board. Within the simulated city or region, what we call a digital twin, the organization can run as many different scenarios as they like to find the best set of options to implement relative to their specific goals. And that's what we've built at Deloitte, a powerful simulation platform for these what-if questions called FutureScape. FutureScape is an agent-based model designed for recreating entire cities or regions, complete with their complex, interconnected infrastructure at scale. By modeling these full-scale networks in one place, we can test how changes or disruptions to part of a network impacts its other parts. And by building a model calibrated to appropriate targets, we can explore the impact of any number of scenarios to inform action. For example, FutureScape simulates how changes to a region's population, infrastructure, and transit service will impact ridership, mode choice, and accessibility. By quantifying impact, transportation planners can then prioritize investments that will improve ridership and quality of service. So, how do we do this? FutureScape blends cloud computing, agent-based simulation, and advanced data science to overcome the limitations of both traditional predictive analytic approaches and the computational demands of agent-based models. This multidisciplinary approach allows us to go end-to-end when answering critical questions about the future, from accessing and processing necessary data inputs to ensuring the agents within the simulation act appropriately to interacting with the simulated environment in real time. We start with a what-if question, and then build a FutureScape simulation in 4 steps. First, we build the simulation environment by ingesting the data necessary to create the digital twin, such as a detailed synthetic population with an activity schedule, a complete road network, transit schedules, and detail about the power and telecom networks. Next, we construct the algorithms that govern behavior of agents in the simulation. These behaviors include pathfinding, reaction to real-time conditions in the simulation, and selection of travel mode. Third, we run the simulation in a distributed way to reduce the computational demand on any one machine. This patented approach allows us to run massive scale simulations relatively quickly without sacrificing detail. Finally, we analyze the outputs and communicate these to our clients using dashboards and geospatial visualizations that make the meaningful insights easy to understand. These results often spark new questions, and we can then make changes to the simulation environment accordingly to test the impact of various scenarios. I want to walk through this process in a bit more detail. Foundationally, simulations are comprised of infrastructure layers, the connections between them, and the agents that travel through them. So we start by building the digital replica of the target area from the ground up by gathering the data layers necessary to create a high-fidelity reconstruction of the real world. For example, our typical road network layer contains information about the number of lanes, speed limits, tolling schemes, and lane restrictions on every road. Similarly, the synthetic populations we use contain detailed demographic and socioeconomic characteristics for every person in the simulation, and we link the activities of the synthetic population to precise coordinate locations. This data comes from open sources or directly from clients or vendors, and in some cases where data isn't readily available, we can create inputs using generative approaches. We can construct synthetic trajectories and activity lists, and we're working on a new process for generating realistic synthetic populations via deep generative modeling. Once the environment is in place, we need to ensure that agent behavior is appropriately governed to create a realistic simulation. We need our agents to obey the rules of the road, both figuratively in terms of decision making and literally when it comes to traffic movements. Agents are configured for simulations using synthetic populations that combine demographic, geographic, and household data to create digital personas that parallel the real world. Then we build custom AI algorithms to drive agent behavior, decisions, and logic in a simulation. For instance, we use a utility-based approach for travel mode selection that can be measured against real-world data. Agents can change their behavior and decisions in reaction to changes in the simulation, but always in ways that are governed by appropriate decision frameworks and physics. One of the key differentiating attributes of FutureScape is our patented scaling engine that automatically assigns simulation processes to available compute hardware and passes information between them to form a single simulated world. This cloud-based horizontal and vertical scaling is key to running rapid simultaneous scenarios. And because the simulation is deployed on cloud architecture, we can launch FutureScape from nearly anywhere, regardless of client in-house infrastructure. With all these components in place, realistic data inputs, tested algorithms that drive agent behavior, and a powerful simulation engine, we can quickly model various scenarios and answer pressing what-if questions. We communicate findings using a combination of dashboards and custom analytics, specifically tailored to client interests, and we do this by leveraging a number of geospatial techniques and tools to analyze the spatio-temporal output data and produce easily understandable results. Now I'd like to show you what a FutureScape simulation looks like in action. We've started up a simulation and rendered the environment, and we can see cars moving around the simulation shown in green, and we're capturing data about routing and car behavior at regular intervals. If I click on a car, I can see its planned route in blue, and I can follow it along that route. In the window that pops up, we can see the details about the car, its occupants, and planned activities. This person is driving alone and heading to work. They have a few activities today, and we can see that in the scheduled portion of the window. In this view, we can take a close look at traffic patterns, which can be very valuable for transportation and regional planners. And we can also explore the interconnected infrastructure layers that we build into the model. First, I'll check out the telecom layer. We can see cell towers and their service areas rendered on the screen. The lines emanating from each tower represent active connections to the telecom network and show that vehicles in the service area are linked to those respective towers. Now I'll switch to the power layer and take a look at the power grid. We can click on any one of these nodes and shut off the power, and then look at the cascade effect of power loss on the surrounding infrastructure. As I flip back to the telecom network view, we can see that this cell tower has lost power, and we notice the number of connections drop to 0 accordingly. Vehicles in the offline tower service area try to connect to the nearest available tower, which could result in a data throttling condition if the tower becomes overloaded. Capturing this kind of cascade effect has obvious implications for improving disaster and resiliency planning. Spatial data science plays an integral role in our ability to build these simulations and deliver results for our clients. Our spatial data science workflows bookend the simulator by preparing or creating data for ingestion to the model and by analyzing and visualizing the model outputs. We now like to take a deeper dive into those specific processes and discuss how we're using advanced spatial data science techniques to improve data generation for more realistic simulations and to communicate complex results in a clear and interactive way. And for that, I'll turn it over to George.
Thank you, Dan. On this portion of our presentation, we're going to be focused on the spatial data science pipelines that we have developed thus far. To begin with our most recent work, a pipeline which we are currently developing is the creation of a synthetic population. FutureScape requires both population information such as individual and household level attributes and a set of activities for that population, the so-called trip schedules, to simulate regional mobility patterns. What we want to do here is essentially to go one step back from the trip schedule generation and develop a solution for generating a detailed population of individuals with realistic demographics and socioeconomic attributes that influence an agent's decision making with respect to travel and activity patterns. So the goal of our population synthesis work is to use the latest technologies to generate a detailed population of individuals for any specified geographic area that is complete with realistic demographics and socioeconomic attributes that influence travel decision making. The challenges that motivated us to create a robust pipeline for population synthesis have been the level of detail of the synthetic population enhances the realism of the simulation. Therefore, we want to incorporate as many demographic, socioeconomic, and behavioral features as possible to take full advantage of the power of agent-based simulation. Second, probabilistic sampling has a tendency to produce a population centered tightly around the mean. A realistic population would be more heterogeneous. And final, a simulation is only as effective as the quality of the input data. So we want to ensure that the synthetic population we use has been subject to a robust validation process. After conducting research for the latest methodologies on population synthesis, we have selected to go with the deep generative models, a very prominent domain in artificial intelligence where it involves deep neural networks combined with progress in stochastic optimization methods. Many earlier approaches for population synthesis use probabilistic sampling, such as Bayes networks, for instance. Instead, we are constructing a variational autoencoder, known as VAE, to generate entire populations from input census data. While VAEs became well known for image processing and generation, we believe that these models are well suited for generating realistic synthetic populations. In a nutshell, autoencoders are a specific type of feed-forward neural networks where the input is the same as the output. They compress the input into a lower dimensional code and then reconstruct the output from this representation. The code is a compact summary or compression of the input, also called the latent space representation. An autoencoder consists of three main components: the encoder, the code, and the decoder. The encoder compresses the input and produces the code, and then the decoder reconstructs the input only using this code. Due to overfitting, the latent space of an autoencoder can be extremely irregular, though, and so we can't really define a generative process that simply consists of sampling a point from the latent space and make it go through the decoder and get new data. So variational autoencoders are autoencoders that tackle the problem of latent space irregularity by making the encoder return a distribution over the latent space instead of a single point, and by adding in the loss function, a regularization term over that return distribution in order to ensure a better organization of the latent space. The use of variational inference and the regularization of the latent space allow this quite realistic reconstruction and generation of the population. For implementation, we have started with using data from the 2019 American Community Survey, known as ACS. So the ACS is a demographic survey program conducted by the US Census Bureau. It regularly gathers information previously contained only in the long form of the decennial census, sent to approximately 300,000 addresses monthly or 3.5 million per year. It is the largest household survey that the Census Bureau administers. Specifically for our first cut of the population synthesis pipeline, we have started by using 20 attributes that capture critical socio-demographic information that we want to generate. For instance, for the categorical data, an example could be educational level, employment type, etc. And some examples on the numerical data could be age, household income, personal income, etc. We are currently developing the VAE using TensorFlow and more specifically Keras. Although the use of the VAE in population synthesis has proven to be a very promising and robust methodology, there are still some challenges that we are currently working on. Although VAEs have been extensively used for computer vision, as we mentioned previously, where the inputs are images, it gets challenging when it comes to socio-demographic data, especially when the data are of mixed types, like in our case, where we have numerical and categorical. As an example of what we're currently investigating is a more specialized neural net architecture or architectures which will be optimal for treating mixed socio-demographic data types. An example that we are currently developing is the construction of a multi-stage mixed input VAE where we sequentially feed the different data types in order to increase the overall performance of the model. After the initial dense layer construction, we pretty much concatenate the categorical and the numerical data. So, in order to conclude this line of work that is in progress, two major results so far have been: first, we have created an initial mode architecture for reconstructing a realistic synthetic population from a VAE trained on census data. Also, in the parallel, we have established a robust validation pipeline based on similarity assessments and anomaly detection methodologies to evaluate the robustness of the model. On the right side here, we can see the regularized latent space of our VAE, represented by two principal components where we can see an indication of cluster sampling groups. Among the several directions that we are considering for further development, two major ones that we are working on at the moment is to further improve the model by both exploring specialized neural net architectures as well as performing hyperparameters optimization so that we can achieve a higher level of realism. And secondly is to merge highly detailed synthetic populations developed using this technique with other simulation inputs to enhance the overall model. A pipeline that we have recently completed is the one for creating synthetic trip schedules. The main objective here was to create synthetic trip schedules for any geographic region in the United States using abstracted patterns of mobility. There are several challenges that motivated us for the creation of this pipeline. The three main ones have been: first, there are not detailed trip schedules available for every city or region, and even in cases where they do exist, political or other constraints might prevent those schedules from being shared across organizations. The second one is an existing trip list from one area cannot simply be ported to another, so generation of a new trip list is necessary. And the third one was that the trip list must be reflective of the travel patterns of the target area in order to produce believable simulation results. Given all these considerations, we have created a 5-step process by leveraging latest technologies in the domain of machine learning for human mobility modeling by using the Scikit Mobility Library. Our pipeline starts by the creation of, first, a Markov mobility diary. So actual trip schedules from different geographies are ingested into the mobility diary generator, which produces a mobility diary containing the sequence of trips made by an agent during a time period divided in time slots, 10 minutes in our case. Second step was a mobility diary learner based on Markov chain which computes a mobility from the mobility trajectories of a set of real individuals. So first, the MDL translates mobility trajectory data of real individuals into abstract mobility trajectories, and as a second step, it uses the obtained abstract trajectory data to compute the transition probabilities of a Markov model, resulting in new synthetic temporal patterns. The second step was the diary-based trajectory simulator modeling framework, where we start with a trajectory generation. Here we transform the mobility diary into mobility trajectories, which captures the spatial patterns of human movements with the use of a weighted spatial tessellation of the territory. This computation is based on the density exploration and preferential return model, and then the explorability of synthetic agents, where this type of modeling allows us to control the agent's tendency to explore a new location during the next move versus returning to a previously visited location. Third step was the trip activities assignment. So after having created an entirely new and synthetic trip list with realistic spatial-temporal patterns of human mobility, the next goal is to detect and assign major activities of these trips. Currently, we're focusing on three main activities: home, work, and other. The home and work locations detection is primarily based on the visit frequency and the time windows. Fourth step was the location specification based on high spatial resolution data. So we're currently leveraging land use information in parcel level data to further specify the location within the admin boundaries used in the spatial tessellation. Currently, the extraction of the synthetic agent spatial-temporal pattern is based on census block groups. By associating the activity types computed in the previous step to the land use information, we end up assigning location to each stop down to the building level, achieving this way a higher accuracy and realism. And the last step was the synthetic agents characteristics assignment. So an integral part of the simulation beyond the spatial-temporal information of the synthetic schedules is the characteristics of persons that aid to the creation of a realistic agent-based model. So we're using census ACS sociodemographic data to draw distributions from and to extract the ones of the synthetic agents based on probabilistic modeling. So currently we can extract and assign the following characteristics as well as derivatives of them, such as age, gender, household income, autosufficiency, and employment and education status. Here is a test where we build a synthetic population of 100,000 people using abstracted patterns of activity from pre-existing triplets. The resulting activity schedule allowed us to simulate a day in a city for which we had no travel pattern detailed on hand. On the map, we illustrate an example of the location plus its activity, which is home, that is the part of the trip schedule generated by our methodology. On the lower right, we can see an example of the data frame that is generated where we have a sequence of timestamps, locations, activities, and sociodemographic characteristics per person. So, in order to conclude about this line of work, here are the three main advantages of this pipeline. First of all, more flexibility. We can create a trip list for any region, which eliminates the need to have existing activity schedules developed via other modeling means. Secondly, greater specificity. We can produce a trip list with spatial granularity that exceeds the resolution of most existing activity schedules used in travel modeling. And the last one is enriched information. We can link fine-grained synthetic population details to the synthetic trajectories, creating a rich input dataset for agent-based simulation. Also, to mention some of our direction for future work on this front, that would be, we are currently labeling activities as home, work, and other. In pursuit of greater realism, we will develop the ability to detect more diverse activities. Could be shopping, eating, university, etc. And second, in order to create trip schedules for larger areas, we are looking and working on the ability to parallelize the critical processes in the pipeline. As we have mentioned in the first section, a critical component of our capabilities and functionality is the interpretation of the simulation outputs and or the post-processed ones via spatio-temporal visualizations. To begin with, for the majority of the geospatial visualizations, we have been using Kepler-GL, a data-agnostic WebGL-empowered high-performance application for geospatial analytic visualizations. The purpose of these visualizations is to explore and analyze the outputs from the simulation as well as to communicate insights to the clients. In addition to visualizing the simulation outputs, we also perform extensive post-simulation analysis to extract further meaningful insights about the scenarios we have implemented. On the left side, we explore the volume of cars here across all the road segments in the simulated environment, which allows us to see where traffic is heaviest. On the visualization on the right side, we look at the most common origin-destination or OD pairs, that the level of activity between them as measured in terms of trip volume. In addition to the static visualizations, we take advantage of the temporal dimensions of the data. The purpose of these visualizations is to utilize the spatial-temporal data to uncover the dynamic human mobility patterns and draw insights. So here on the left side, we can see an example of the OD trips over time. By exploring the temporal dimensions of the data, we're able to discern both the geographic distribution of the underlying dynamic systems as well as the spatial-temporal signatures of the human mobility. On the right side, we visualize the level of activity over time. By clustering the number of activities in equal-sized geographic bins, we can visualize the level of activity occurring in any given location during the day. So, as we have showcased today, FutureScape is an agent-based simulation tool for answering critical what-if questions for large and dynamic systems without sacrificing the complexity or scale. Our spatial data science work is an integral component to the overall architecture. And with that, thank you so much for joining today. We have a few minutes for Q&A. Thank you.
Dan and George, thank you so much for your presentation, and what a powerful tool you presented today. I believe we have a couple of time for some questions, if that's all right with you.
Of course.
Awesome.
Absolutely. Thank you for having us here.
So to start off, what variety of data formats can FutureScape accept, and how large of an area can you simulate, and how long does that take?
Yeah, so I'll take that first question. So we can currently accept, we've designed a tool to be as flexible as possible to accept a lot of different data sources. So in terms of synthetic populations, we can accept CSV, text file, for geospatial inputs, shape files, GeoJSONs. We've currently built simulations as well for fairly large areas. We like to focus on entire cities or regions. And so as an example, we work with a client in the United States where we built a simulation for 6,000 square mile area, a population of over 3 million people. And at the end of the day, that kind of simulation, once configured, will run in about 2 to 3 hours for an entire 24-hour period in the simulation. So it's relatively quick.
All right, next question is, what are some advantages of using deep generative modeling versus more traditional probabilistic models for population synthesis?
Yeah, absolutely, and happy to address this question. So to begin with, let me take one step first, back to define these two categories because it's important. So to begin with, the probabilistic models, this is a class of models where we can define the explicit structure of the relationships between the variables of interest and other hidden variables and proceed to estimate parameters based on these assumptions. And we have some really typical examples here, like the hidden Markov models or the Bayes nets, etc. So the deep generative models, so it's a class of probabilistic models in which we parameterize the data generating process with deep neural networks, either explicitly modeling the relationships between the latent and observed variables, or implicitly with adversarial training. And here we have two very characteristic and powerful techniques or algorithms. The one is the GAN, or generative adversarial models, and the VAEs, the variational autoencoders that we're using here. So now back to your question about the advantages of the VAEs specifically over the typical probabilistic models, and specifically for our application, because it goes by application. The VAEs can generate synthetic population with potentially hundreds of mixed continuous and categorical attributes. So this opens the path towards modeling of a population with a very high level of detail, including smaller zones, personal details, and travel preferences. Also, really important here is when it comes to model performance, and more specifically about the runtime. So the advantages of the VAE over the probabilistic modeling becomes really evident when the number of attributes increases as it scales quite nicely. And the last one so far is that the VAE allows for the growing out of sample, as we call it, agents, which are different from the agents present in the training data, but preserve the same statistical properties and dependencies as in the original data. So it can be used pretty much to address the sampling zero problem, as we call it. So this ability of generative models to generate out-of-sample agents can be used to explore a richer, if you want, set of modeling scenarios.
Got it. Thank you. The speed, scale, and granularity your model can get is really impressive, I have to say. And as you were presenting the Q&A, we have quite a few questions. I think we have time to at least get to one of them. And then after the session, of course, Dan and George, you can go in the chat and answer some of the other ones that we didn't have time to address. But could you elaborate on the validation pipeline you mentioned? How close are the results of the simulation to real behavior observed in benchmark data?
That's an excellent question. First of all, before I reply the question, just to let you know that we are tackling the validation in it has several components. So to begin with, one important component or dimension in terms of reality that we evaluate is the ground truth, which is the actual census data versus what we produce. We validate this through statistical testing, similarity scores, multivariate analysis with density plots and histograms. And then the other aspect, which is equally important, is to avoid the outliers, which is unrealistic personas and agents, which in this case, we perform some really sophisticated anomaly detection techniques where we want to detect, as I said, unrealistic persons, but you have to, what is challenging here is that you have to incorporate all the dimensions of this synthetic agent, which is 20 different attributes, like the combination in total has to make sense.
Thank you. Sounds like a very complicated process. And as mentioned, Dan and George will be able to follow up with any unanswered